So we're going to go ahead and introduce our last group presenting tonight. The name of the group is the Puzzle Assembling Robot, and this group is advised by Dr. Allison. So could the first presenter within the group please activate your microphone and your video? Again, please remember to introduce yourselves before each of you start your presentations, and be sure to hand it off to the next person.
All right. Hi, everyone. I'm Alex Kennedy. I am the team leader for the Puzzle Assembling Robot Senior Design Team. We're advised by Dr. Allison, as Dr. Barty said. So just to give a brief overview of our entire project, our ultimate goal is to generate interest in the mechanical engineering department and then the robotics minor. Our project is a continuation of a 2019 senior project. It essentially operates in the same manner as the 2019 project. And as you'll see in the video here, it will identify each of the individual puzzle pieces using a vision system and camera. It's able to figure out where to pick up the pieces using that vision system. And then it's able to pick and place each of those parts. And after that, it does a little dance to celebrate. So some key improvements that we've made to our project, this is sort of our contribution. We noticed some issues with the repeatability of the gripping system, so we've addressed those. In addition, we've had some issues with the accuracy of the vision system, so we've made changes to the part identification and assembly code in order to address that. Finally, we have improved the overall safety of the system through the integration of Allen Bradley hardware, specifically a programmable logic controller and a human machine interface, or PLC and HMI. So now I'm going to hand it off to Brad Mazok, and he's going to talk a little bit more about our mechanical design components.
Hello, everybody. As Alex said, I'm Brad Mazok, and I work on the mechanical design team with Cameron Good. And today I'll talk about our vacuum gripping system. And so basically, we started out with a mechanical gripping system that was inherited from last year's project. And so we heard it had a 9 out of 10 success rate, and so we were wondering why it wasn't closer to 10 out of 10. So we started testing it, and then we saw why it wasn't closer to 10 out of 10. One of the big issues here was that it would rotate when we would pick the puzzle piece up until it hit the stop, which is red, circled in red. So the farther away the stop was from the top of the puzzle piece, the more it would rotate. And then there were other issues involved that will be compared to this vacuum gripper that was tested also. So this vacuum gripper we got from Dr. Allison. It was just laying around in stock, and so it used all PAB components, and we did similar tests to it that we did for the mechanical gripper. And so we were not excited about the vacuum gripper at first. We thought it wouldn't be able to pick up the pieces because engraving, etc. But we were actually very, very pleasantly surprised when we started testing it. Like, it just blew our minds how well it worked. And so it came down to decision time. Do we choose the mechanical gripper or do we choose the vacuum gripper, which was something new? We ended up deciding the vacuum gripper for these 4 main reasons. One of the reasons was because of the draft on the sides of the puzzle piece. This was so that the puzzle piece would be easier to assemble. The draft tapered towards the bottom of the puzzle pieces. And so because the mechanical gripper gripped the side of the puzzle pieces, which is where the draft was at, there would only be a line of contact versus a surface of contact. But the vacuum gripper would have a surface of contact, and in the engraving, it would just deform into that surface. And the second reason was that you can fully lower the vacuum gripper. You can fully lower the puzzle piece using the vacuum gripper, while the mechanical one you can't, because if you try to lower it into the puzzle box, it'll either hit other pieces or hit the puzzle box. And so this was obviously an issue. And so we had to drop the puzzle pieces, which would cause reliability issues because the pieces would bounce onto the puzzle box and like it would be in a different location. And so third reason was that you could grip the center of mass with the vacuum gripper more accurately, while with the mechanical gripper, you have these certain pick points, which are usually away from the center of gravity. And so because of this, it would rotate, and so it would apply a torque to the vacuum gripper or the mechanical gripper. And so the vacuum gripper was nice because you could actually put it on the center of gravity. And so unlike the mechanical gripper. And then last was quality preservation. And so basically the both of these were pneumatic grippers, and the mechanical gripper would gouge sides of the puzzle pieces, which was not good at all. And vacuum gripper, the worst it would do was leave a spot on the piece. And so because of the 3 reasons before, we decided to not optimize the mechanical gripper to decrease that gouging, which optimizing would be just decreasing PSI levels, but we'd already decided on the vacuum gripper, so there was no need on that. And then finally, when we went full into the vacuum gripper, we decided to have a PIAB representative come look at our product. He actually lived in Erie, but he looked at our product and he decided that everything was good except for the vacuum cups. And so we ordered 5 vacuum cups, different materials and profiles and shapes, etc. We ended up deciding on the one on the left, which is a 10 by 30 millimeter vacuum cup made of polyurethane. And we ended up deciding on this one because it was reliable and because it could hold more weight. And so now I'll pass it on to Cameron Good, and he will talk about the HMI PLC box as well as the lighting fixture.
Thank you, Brad. As noted, my name is Cameron Good, and I'll be talking about the mechanical design with regards to our next area of improvement of our project, which includes improvements on our vision system. A custom LED panel for backlighting the puzzle pieces, which you'll hear about shortly from our vision team, was needed to design fixturing to correctly apply it to our base plate. The picture on the left shows a concept drawing with design requirements, including a manufacturer recommended spacing between the light panel and frosted plexiglass diffusing panel. This diffusing panel is meant to even out the light, providing flat backlighting for the puzzle pieces. We created a Z-clip, so to speak, that holds the panels in friction fit and creates the diffusing space while holding them securely in order under our rotating table. The view on the right then shows a final CAD model that was used to 3D print 3 of these fixtures. Now, just to show the layout, we used 3 clips to provide adequate support and a configuration to not interfere with the backlight coming through the designated puzzle placement locations. The picture on the right shows a side view of one of the installed Z-clips. And one final area from a mechanical design perspective was the creation of a controls cart. Since the robot cell used for this project is also regularly used in the classroom setting, we needed to create a way to easily move back and forth between the classroom setup and our presentation configuration. Thus, the requirements resulted in the cart being mobile, yet rigid to house all of our controls components. This includes our human-machine interface, programmable logic controller, power supply, and network switch. All of these elements will be explained further very shortly, but the HMI is essentially a viewing screen where an operator can give commands to the PLC and the robot, as well as explain to the operator the status of the different sections of the program that are currently running. Since this project was also put into place to allow prospective students or other guests to get an insight on some engineering aspects that our department works with, we decided to keep an open viewing concept with the lower half of the cart. The left picture is our final CAD model utilizing an aluminum 80/20 frame to match the robot cell. The frame is on 4 caster wheels with adequate internal framing for mounting and an external steel electronic enclosure that was purchased to house the HMI. The right picture shows a final build of the cart where you can see the HMI offset at an angle that allows for easy viewing for both the operator and onlookers. The only parts we did not complete were Lexan side panels, which are a form of polycarbonate paneling material, and yellow channel covers that would match the frame of the existing robot cell. Now I'm going to pass it off to Daniel Walton, and he'll explain some of the vision team's contributions to this project. Cam. As Cam said, my name is Daniel Walton, and I'll be talking a little bit about the vision and programming that took place. Our first redesign took place with regards to the backlighting. A picture of last year's backlight can be seen on the right of the screen, and it consists of 7 light pucks held together using a 3D printed frame and electrical tape, along with the mediocre appearance and the design poorly distributing the light. Additionally, its lower brightness quality made part identification less accurate and take much longer, and because of the extra wires and poor choice of materials, this design was hard to install and remove as well. So the backlight was redesigned using a custom manufactured LumaSheet light panel, and this light panel consisted of LEDs mounted along the interior and exterior surfaces and uses V-Groove technology to evenly distribute the light across its area. The number of LEDs was chosen to optimize the brightness and uniformity of the light diffusion. This technology gave us about a 6-fold increase in brightness while maintaining a highly uniform diffusion. The new backlight was then cleanly fixtured to the back plate and for easy installation and removal. Additional area beneath the table was encompassed by this backlight, and in a minute I'll talk about how this increased the versatility of our box identification system. There was, however, one complication. The dimmer operated using pulse width modulation. Because this frequency was on the same order as our camera's exposure rate, the vision system imaging often appeared black when dimming occurred. Unfortunately, and fortunately, the system works well without any dimming, so the brightest setting can still be used. Our next redesign was the puzzle box. Redesigning the puzzle box was very important for obtaining a high degree of accuracy for our system. During the operation, all the pieces must be properly placed with respect to the box. The previous design was made of wood, which tends to warp with changes in heat. And furthermore, this design was identified using ambient light in conjunction with the black line around the interior of the box. This method did not allow us to see much contrast with the identification. Additionally, errors were high and score thresholds poor. Using Fanuc's recommended design requirements, we were able to redesign this year's box to fit within those. So the new box utilizes the extra size of the backlighting, so light can shine through the holes in the box, and this creates a vastly improved contrast, better fit error, and a higher overall score. Next, we improved the improved design of the backlight aided our part identification. During this process, all complex geometry and blurred edges were masked out, and the high contrast of the new backlight enabled us to do very little masking, and this gave us a faster and more accurate part identification time. So now I'm going to pass it off to Billy Swatton. He's going to go into more detail on what we did to program the
robot. Thanks, Dan. So I'm Billy Swatton, and I'm going to be focusing on 2 aspects of the programming which we've been working on for the last 2 semesters. The first one is calibration, and the second is the main teach-dependent program for the FANUC. So one of our main goals for the project was improving reliability of the robot, and this was in the form of calibration. So FANUC has many forms of calibration, and there are 2 that our robot uses for our particular assembly program. So number 1 is the frame calibration, seen on the right. It was implemented by the previous team, and this defines a user frame, which is helpful for picking up puzzle pieces. It's essentially a coordinate system with an origin on our turntable. And to add to calibration, before the quarantine, we had been checking our turntable for accuracy and consistency, because it's important that both sides are at the same height when we rotate the table around 180 degrees, especially for the vacuum system. So we also added perspective calibration, which is seen on the left, and this affects our camera's millimeter per pixel count. So this is a two-plane calibration where the dots on our grid are scaled in proportion to the distance between our planes. And so this is helpful for identifying pick and place points, which I'll explain later. So position training is another big step in calibration. It's essentially the process where the robot is trained to place pieces in the box correctly. And there are also two steps in this procedure we worked on. Number one is the part establishment in IR vision. In this process, we establish coordinate systems on the trained part with data like yaw, pitch, and roll in reference to the camera. So the robot can then use this information as reference data later. Second is the calibration of the vision position registers. This was the really time-consuming part of the calibration. So we'd move the gripper to the part and train what's called a pick point. We then turn the vacuum on and pick up the piece. And finally, we drag the part to the appropriate place in the box, establishing a place point. And this is quite difficult to get right and requires a lot of time. So finally, I want to discuss just the overall vision program we ended up with. And this is a top view process flow for the assembly program. And so I'll just describe the basic components. So it starts with the puzzle main script, which provides the basic layout for the sub-assemblies and has a lot of variables. Vision circle scan is going to look at every position in the semicircle and identify if there's a part or not. And then puzzle select piece is going to assign each piece to the appropriate registers so the offsets are correct. And finally, a puzzle pick actually moves the pieces from the light table to the puzzle box. So here's just a basic program example of how one might design a simple vision script. And this was part of our testing. So there are three basic items in here. Number one, in the black is the initialization. So these are just basic setup parameters for the robot to know what to do. Second is the vision identification script. And we have several lines here dedicated to finding trained parts and getting those vision offsets that we need for later. And then finally in the yellow are the move and IO commands to turn the gripping system on or off and to move the part into the puzzle box. And so altogether we'd be able to put one piece together with this code. So next I'm going to hand it off to Noah to talk a little bit about our interfaces.
Thank you, Billy. As Billy said, my name is Noah Vroman, and I worked on the PLC and HMI sub-team along with Alex Kennedy. So as Alex said at the start of our presentation, one of the main focuses of our project was really to build and expand upon the previous year's project, and the PLC and HMI team did that through a series of hardware additions. Our new hardware additions to the project include an Allen Bradley Compact Logix PLC, an Allen Bradley Panel View +7 HMI display, 2 magnetic actuating door switches, 1 diffuse laser sensor, a 24-volt power supply to power all of the above components, and a network switch that will allow communication between the PLC, HMI, FANUC robot, and a laptop for programming purposes. So what exactly is a PLC? PLC stands for Programmable Logic Controller, and basically it monitors digital signals that it sends and receives from other devices. While running a program, the PLC continuously checks the state of each signal, such as the outputs from the door switches and the laser sensor. The PLC then sends out appropriate signals to other devices depending on an input signal status. So since this project will be used for a variety of student-oriented events, safety was a large concern for us. This is why we chose to use the PLC as a safety monitoring device, and a good example of how it works is with the magnetic door switches. The door switches, mounted by the handles, here circled in red, send a signal on whether or not they are activated, which translates to the door being open or closed. If the door is closed, the PLC sends a signal to the robot allowing the program to run, but if the door is open, the PLC sends a different signal to stop the robot's motion. Similarly, the turntable sensor, which would be the laser sensor, circled in blue, would be mounted there and would send a signal on whether or not the turntable was in position. If it was in position, the program would be able to run, but if it was out of position, the robot's motion would stop. So onto the HMI, which we can see here mounted on the cart. HMI stands for Human to Machine Interface and basically functions as an interactive touchscreen for inputting commands into the PLC and also for displaying program information. For our application, the HMI was to be used to start and stop the assembly program, provide informational screens on how each part of the project operates, give a visual status update on the assembly progress, and also show an alarm log listing safety notifications, such as when an e-stop button was pressed or a door was opened while the program motion was running. Unfortunately, due to COVID-19, many features were not implemented before our time concluded at the college. So these are a few conceptual layouts that were developed in PowerPoint to embody our vision for the HMI system. The screen in the upper left would have been the start screen that would have been displayed before the program was running. And after the start button was pressed, the screen in the bottom right would have been displayed, which would have been shown while the program was running. This would show which parts were correctly identified and assembled. Now, Alex Kennedy will explain what we use to allow the different parts of the project to communicate with each other.
All right, thanks, Noah. So yeah, I'm going to talk a little bit about our device communication. So this is what allows us to take all of our different individual components that we have in the project and help them to communicate information between each other. So the two major components of this that we need are a network switch, which is pictured in the background of this slide with all of our devices plugged into it via Ethernet. And we also need static IP addresses set up on each of our devices. So to kind of explain how this works, I'm going to use an analogy from the mail system. So whenever you want to send mail to somebody, they need to have a place to receive the mail. So either a house or a business or something like that. They also need to have some sort of a home or a street address from which they can receive their mail. And then also you don't usually send mail directly to somebody's house. You have to send it through the post office. So in our system, the houses or businesses are analogous to our individual devices. The IP addresses are like your street or home address, and then the network switch acts as your post office. So why do the IP addresses need to be static? The reason for that is similar, again, with the mail analogy, is if you want to send some mail to your friend and maybe he just moved to a new place and you don't know his address, you're going to have a really hard time sending him some mail. In the same way, if our devices don't know the IP addresses of the other components in the system, it's going to be really hard for them to communicate data between them. So the reason that we set up the static IP addresses is so that all of the IP addresses stay the same regardless of what network port that we're plugging into. So for example, when we move from our senior design lab for testing and move down to the IM room to do a demonstration at some sort of a student event, we would still have the same IP addresses rather than them being reassigned whenever we move to a new network port. So what is the information that we want to send between our devices? Well, the answer to that is input and output data, or I/O data. So on this slide, I have on the left is the FANUC end of the I/O, and on the right you see the Studio 5000 PLC and HMI programming software. So at the top, I have circled DO1, which stands for Digital Output 1. And let's say that this is connected to an emergency stop button on the robot. Through the FANUC Advanced Ethernet IP package that we purchased, we are able to communicate between these two different forms of input and output data so that whenever a state change in this emergency stop button is pressed, not only will the off turn to an on the left, but also on the right side of the image, that the other data point that I have circled there, in the second column, that 0 will change to a 1. Now with that information, we can program our devices to perform a specific action. So in this case, if the emergency stop button is pressed and that 0 turns into a 1 on the right side of the screen, we are able to maybe send an alarm message to the HMI to alert the user that there's a problem. This is the main functionality that we wanted to use this package for, communication between the HMI and the robot controller, because we want to have the student be able to start and stop the program from the HMI and some sorts of things like that. Unfortunately, we were unable to implement this concept before we had to return from campus. So this is still in the conceptual phase, but ultimately this concept should work. So just to give another general summary of all of the components of our project, it comprises of a robotic system with a FANUC industrial assembly robot, and then that assembles the puzzle pieces with the help of a vision system and 2D camera. In addition, our goal is to generate student interest in engineering and robotics. And the 3 improvements that we have made in this system over the previous system have been replacing the part gripping system, improving the computer vision capabilities through changes to the assembly and part identification code, and also improving the overall safety of the system through the addition of our Allen Bradley hardware, the PLC, and the HMI. So that concludes our presentation. Are there any questions?
Thank you very much. Very well done. We're going to go ahead now and open the floor to questions. So if you have any questions, please indicate in the chat, or if you are joining from a browser, feel free to just activate your mic and ask your question. There is one question that I usually like to ask, and it is, what would you say for you guys this semester was the most challenging aspect of this project?
Yeah, I mean, speaking from my own experience with specifically working on the PLC HMI side of things, it's just the learning curve. We didn't have any prior experience with PLCs and HMIs, or programming them, or learning how to operate them, or even really any of the logic that goes on behind them. So it just took a lot of time of research and just digging into YouTube videos or, documentation on that sort of stuff just to get the hang of it. And then you had to start working on implementing it. So just the quick turnaround on that was pretty difficult, but I can let some of the other team members speak to their own experience as well.
Yeah, I would say similarly for the FANUC robot. Actually, we had some training in a previous course with it, but a lot of what we did with the vision system was brand new to us. And then another thing that the vision system team at least had an issue with was the part pick and place points. It was just really hard to get accurate points so that the puzzle assembled every single time.
Thank you. Any other comments in regards to that question? Okay, thank you very much. Dr. Allison had a comment that he'd like to make. Go ahead, Dr. Allison.
Yeah, this is much more of a comment than a question. I just wanted to second what Alex had to say with regards to the learning curve associated with PLCs and HMIs. In general, the college and the mechanical engineering department in particular would like to enhance our expertise in the area of factory automation. And at the heart of factory automation are PLCs and HMI systems. And so when we got involved in this project, none of the team members, nor myself, had any experience with them. And for this particular team, as well as for the BPMI team that presented last night, they really did have a steep learning curve. They worked hard at it, and I think made really great progress, both teams.
Thank you for that. So now Dr. Anderson had a question he would like to ask. Go ahead, Dr. Anderson.
Yeah, I just have a question about your backlighting. and mostly because I'm curious because I use backlighting. How did you feel about how the V-Groove backlighting worked? How did you spec that out? How expensive was it? Did it work the way you thought it would work?
Yeah, I'll let Dan handle that question. Dan and Billy worked specifically on the backlighting. So go ahead, guys.
Okay, I'll talk about that. And I'm gonna have a hard time remembering what all your questions were, but the V-Groove technology, I'm not sure if you're familiar with it, but it kind of uses a V shape that changes in height as it moves across the area, and it distributed the light very well. We actually were given an extra diffusing panel for it anyway, which we only used one of them because it worked so well. The cost for it was pretty high. We didn't go with like a company that is known for making backlighting in particular, but the company's name was Evolite, and I think it cost somewhere in the realm of, I want to say $600, but Brad would know more about the actual cost of it. Does that answer your question? Were there any other ones?
Yeah, did the panel come separate from the LEDs, or did you guys have does it come with it? Like, do you have to build something, or does it all come as a thing you just kind of plug in the wall?
Basically comes as something you plug in the wall. Yeah. And we sent them the design that we wanted for it, and they were able to come up with the number of LEDs and everything that we would need for that brightness. The one issue that I mentioned we had was with the pulse width modulation of it. If you're using a camera, you're going to want to run it at the highest brightness unless you have a different means of changing the dimming.
Yeah.
Cool. I was gonna add to that too, that so we sent them a design and so they were able to machine it from, like, I guess, a bigger piece. So that was pretty cool.
Real quick, Dr. Henderson, the picture that you see on the question slide, that is a sample that was sent to us without a diffusing panel. So you would see the grids of the V-Groove unless the diffusing panel was used like we had. So it did work very well. So
great.
Also, for all of the lighting equipment that was involved, it was $792.
Great, thank you.
Any other follow-up to that question? All right, well, thank you. Any other questions from anybody? Okay, well, thank you very much. Oops, I'm sorry, there was a question that popped up. Dr. Klaus has a question. Go ahead, Dr. Klaus.
Sure, thank you. As you think about possibly having this assemble a different puzzle, how much time and effort would it be necessary for you to have it learn and be able to do that with something else? We'll assume the same number of pieces.
Well, actually, I'll take part of it. The vacuum gripper, because it's so robust and it doesn't have to be a certain distance. Like the mechanical gripper, it would close and open a certain distance, but the vacuum gripper, you could shape the pieces whatever you want, and it should still work. So that's what I would give for the vacuum gripper part of it.
So, what I was going to say to that is, it took me and Dan like quite a few days to get like even a couple of pieces in the right spot. And I think that would be helped. I think the table is a little bit less than level. So I was saying before that we were trying to like level that before the semester was over. And I think if you had that down, you could maybe do it in an afternoon. But from where it stands now, what we would have to do, it would take several days, I would say.
Okay, thank you.
Thank you for that question. Any other questions for this group? Well, thank you. You guys did a wonderful job.